My name is Marco Serrato. I am entering my third year here at UC Santa Barbara in physics, and I'm working on digital control electronics for optical gyroscopes under Dr. Daniel Blumenthal and Suraj Gunavadapur of the ECE department. So we start by asking ourselves, what exactly is an optical gyroscope, or what does it do? So gyroscopes have traditionally been used as rotational sensors. Optical gyroscopes are used as highly sensitive rotational sensors. So they use loops of fiber optic wires in which we counter-propagate light in both directions, like so. And we observe how they interfere. So in this case, they both meet up at this point, for example. And so taking those loops and, for example, spinning them, this is the case spinning, we can see how they interfere differently. In this case, they did not meet up at the exact same time, so they are in different phases, for example. And so seeing how the differences in how these situations interfere, we can use them to basically detect rotational motion. And so because they're so precise in what motions they can detect, they're used extensively in aircraft navigation. However, there's also potential uses in other industries, such as autonomous vehicle control, for example. So this is a block diagram of the optical gyroscope. So light travels from the source through the circulator, which allows the light source or the light wave to travel in certain directions depending on where it's coming from. And it's split here at the splitter. And so the light source goes in both directions and it counter-propagates inside the fiber coil. And this phase modulator applies a phase bias to the light wave to bring our operating point to zero. So when it's at a standstill state, at the photodetector will detect the voltage of 0. And so it makes it easier for us to detect changes in voltage levels when you rotate the apparatus. There's also a few important variables that we should at least hear about. So the first is something called the scale factor. So the scale factor relates the rotational rate of the optical gyroscope to the voltage that is detected at the photodetector. And so this is sample data that I processed using MATLAB, so it wasn't done by me, but it demonstrates that the scale factor is pretty linear in an optical gyroscope. So that's pretty important. Next is something called the proper frequency. So the proper frequency is the frequency that we want to bias the phase modulator so that we can ensure that the optical gyroscope is functioning at its most sensitive level. Lastly is something called the Allen deviation. So the Allen deviation measures the frequency stability of the optical gyroscope. And so why it's important is because we can apply the Allen deviation and use it as a sort of noise error analysis technique. So we can view the systemic errors that are present within the optical gyroscope. And so for our project, the main goal is to miniaturize the bulky optic gyro models into the smaller on-chip versions. And so in terms of size reduction, the scale that we're looking at is something that is equivalent to the size of a baseball to something that is equivalent to the size of a quarter. So it's a pretty sizable reduction. We also want to create a model that is a low-power draw model. So the problem that might arise from this is that in a light source such as a laser, a low-power draw tends to cause instability in the source. And it goes without saying that the chip itself also has to provide precise measurements, as that is kind of the whole point of an optical gyroscope. And lastly, we want to use digital control electronics, which is actually what I've been focusing on, and I'll be talking about that. So digital control electronics, what this means is that we're using external hardware that handles digital signals to kind of affect the system. In this case, what I'm talking about is something called a field programmable gate array, an FPGA. So this is an example of an FPGA. This is the Vertex 4 model that I've actually been working with. And so the FPGA can be used for many different purposes. It can be used to emulate many different digital circuits. In this case, what I've been using it for is to emulate, or basically using it as a function generator. So I've been using it to apply I've been synthesizing different frequencies with the FPGA that is to be applied to the phase modulator. And so this goes back to what I talked about proper frequency. If we can apply the correct frequency to the phase modulator using the FPGA, we can maximize the sensitivity of the optical gyroscope. And so from this we can see that the FPGA is a pretty important tool to what I've been working with. But equally important are the tools that go into making the FPGA work as intended. So this is the FPGA again. And so by itself, it's not necessarily a very useful tool. It can't really do much in its normal state. And so its usefulness is brought out when we pair it up with a programming language that is called Very High-Speed Integrated Circuit Hardware Descriptive Language. And just because it's a mouthful, we abbreviate it to VHDL for convenience. And so VHDL, how it works is it's a hardware descriptive language that is used exclusively for FPGAs. So this is a sample code of VHDL. And basically what it does is it explains a hardware setup. So when we apply this software to this hardware, it changes what circuit the FPGA is emulating at the moment. And in order to apply VHDL, I've been using something called Xilinx ISC Design Suite version 14.7. So you might note that Xilinx is also the corporation that designed the FPGAs. And so this software that they provided is a native FPGA programming and assignment environment. So using Design Suite, I can code a VHDL program, I can generate a programming file, and then I can apply it to the FPGA. But it also has another program called ISIM, which works as a VHDL simulation software. So I can use ISIM to model the behavior of VHDL code that I might have written in the Design Suite program. And I actually want to talk about traces now. So what I've been working on is programming the FPGA to synthesize different frequencies. And so I just want to show you an example of one such code or program that I wrote to demonstrate. So on the top here is a simulation trace. So using a 100 megahertz frequency clock reference, I've been synthesizing in this example a 5 megahertz signal. And so this is the simulation. So the process goes from writing the code to simulating it to then assigning it to the FPGA and connecting that to an oscilloscope to determine just how well the code translates to the actual hardware. And so this is the oscilloscope trace of this simulation. And so it looks a little different, but they are both 5 megahertz wave. So the process has been done from beginning to end. Another thing that I've also worked on is changing the duty cycle of the signal. So the duty cycle basically indicates the amount of time that the signal is left on an on period versus how long it's left on an off period within its natural cycle. So these two are simulation traces where I've used a standard 50% duty cycle wave. So in its natural frequency, it's on for half the time and off for half the time. And so I shifted it so that it would be at 75% on the top and then 25% on the bottom. So changing the duty cycle can actually affect the power consumption of the device as well. So it's just something that I've also worked on. And so that's well and all, so I can do that, but just how accurate is the code that I've written? Does it perform as well as optimally as it could? And so just to answer that, I've been working with something called IP cores. So to simplify, IP cores are sort of pre-coded subprograms in the VHDL libraries that I can that I can click or I can use, I can configure certain settings, and I can generate these sort of instant codes that I can download onto the FPGA to perform certain things. So I can use, for example, a frequency synthesizer, sort of what I've been coding. And so I wanted to compare the custom codes that I've written to the IP cores just to see how accurate my code is. And so these are two more examples. So this is a 10 megahertz signal that I've basically done, and this is the 25 megahertz. And so I've compared them to the same traces from using IP cores that have been optimized so that they are supposed to give the same output. As you can see, aside from certain zooming in or zooming out with the oscilloscope trace, they match up perfectly, which indicates that the code is working as it should. And so you might be asking, okay, so why are you doing this? So my goal actually is to create a program that allows me to dynamically change the signal frequency. And so if I can do this, I can sort of search for the proper frequency in a more efficient manner. So I don't have to restart the devices or the trace, and I can just do it on the fly. And so just to demonstrate what exactly, or why exactly is important, I want to show you something. So this is an example graph of frequency versus voltage of the optical gyroscope. And so this isn't my data, it's pre-recorded, but this is just to show you what I'm trying to say. So here it's noted in the graph that the proper frequency is found at this frequency. So it's found at the lowest voltage in this graph. Now, look at the frequency. It's 7.96 megahertz. Since we start with a 100 megahertz clock, it's kind of difficult to just at a glance estimate where the proper frequency might be or how to code a program that lets you synthesize that frequency. And so I want to use the dynamic signal that I'm intending to create to be able to search for the proper frequency just by dividing the frequency and multiplying it, for example. So by doing that, I can in a more efficient manner search for the proper frequency. So currently, the signal that the FPGA is synthesizing can be changed statically. And by that I mean that after reprogramming the device or restarting the equipment, I can change the frequency if I'm using certain inputs. The problem here is that I don't want it to be restarted or reprogrammed. I want to be able to change the signal dynamically. I want the divisions to be compounded. So if I press a button, this 100 megahertz signal should be modified. And if I press another button, then that modified signal should then be remodified. So I don't want to have to press the button and then restart it so that it sends the signal and then restart it again, because that might erase the modifications already done to the signal. And that's currently where I'm at. So for future research and testing, in control electronics, I want to test the FPGA some more, and also integrate the signal with the optical gyroscope to test for the sensitivity. In terms of error analysis, I also want to see if we can apply the Allen deviation to the optical gyroscope. And in general, I want to also attempt to establish the closed-loop circuit of the optical gyroscope, and also test the gyroscope from beginning to end. I want to extend my gratitude to the following groups of people. They've really been a big help this summer. They've really granted me some amazing opportunities this summer, and I want to thank them all. And if you have any, I'll be taking questions. Thank you.